All right, in this worked example, it reads, an alpha particle moves in a straight line through a vacuum with a constant speed of 4.1 times 10 to the 6 meters per second. The alpha particle enters a uniform electric field at point A, as shown in figure 4.1. The alpha particle continues to move in the same straight line until it is brought to rest at point B by the electric field. The deceleration of the alpha particle by the electric field is 2.7 times 10 to the 14 meters per second squared. State the direction of the electric field. You have to know that an alpha particle is positively charged and that the force that's exerted on the alpha particle is in this direction. The direction of an electric field is the way that a positive charge moves if placed in the field. So because the force is acting to the left, and that's the way a positive charge would move, the alpha particle is positive. We know that that's the direction of the electric field. So the direction is to the left. Question goes on to ask you to calculate the distance AB. So the distance between A and B, we could solve kinematically using equations of motion. So it's sort of a uniform electric field means that there's going to be constant deceleration. So we can relate the final velocity to the initial velocity and the acceleration with the displacement. The displacement vector is the distance AB with this equation here. Because it's brought to rest, the final velocity is 0. The initial velocity was given as, I think it was 2.1, 4.1 by 10 to the 6. Meters per second squared. I'm sorry, meters per second, and the quantity is squared, in this equation, plus 2 times the acceleration is 2.7 times 10 to the 14. So you're solving there for S, the displacement vector. When you subtract this term from both sides, it's negative over here. You really are dividing by 2a. It's a negative acceleration. And so you're dividing two negatives to get a positive sort of displacement vector, deceleration. If this to the right is assigned as the positive direction, then we know that the force and therefore the acceleration is acting to the left against in the same direction as the electric field. If you type that in your calculator correctly, you should get 0.031 as the correct answer for the distance there, 0.031 meters, so about a little bit more than 3 centimeters that alpha particle will be brought to rest. All right, the question goes on to say, calculate the electric field strength. And so we can calculate the strength of the electric field as the force per charge. They don't tell us the force that's acting on the alpha particle, but we should be able to calculate the mass of the alpha particle and multiply it by the deceleration, and that's going to be equal to the force. So F equals ma divided by q. So the mass of an alpha particle and the charge of an alpha particle are calculable. An alpha particle consists of 2 protons and 2 neutrons, and a neutron and a proton are both close enough in mass that we unify their mass together in what's called a unified atomic mass unit. So there's 4 unified atomic mass units in an alpha particle. The unified atomic mass unit has a value of 1.66 times 10 to the negative 27 kilograms. So you calculate the mass like that. The charge on an alpha particle, well, there's 2 protons in the alpha particle, and so there's positive 2 elementary charges. You may recall that elementary charge is 1.6 times 10 to the negative 19 coulombs. And so the mass is 4u times the acceleration a. The charge is 2e. Then substituting in values, 4 times u, where u is that. The acceleration is still 2.7 times 10 to the 14 meters per second squared, 1.66 by 10 to the minus 27 for that, 4, 2, 1.6 by 10 to the negative 19. And if you type all that in correctly, you should get 5.6 million. And then the units are either, volts per meter, so voltage divided by distance is the other way to sort of think about electric field, equivalent to a Newton per coulomb. So I think the units that they've got on the answer line are volts per meter, so it'd be 5.6 million for that one. 5.6 million volts per meter. right, part D here asks you to sketch the variation with time t of the momentum of the alpha particle as it travels from point A to point B. It says numerical values are not required. Now, we could have calculated the time using the definition of acceleration, in other words, v minus u over t. Since we knew the final initial velocity and the acceleration, we could have figured out the time and then plugged that back into another equation of motion to solve for the displacement. We avoided that by using, this equation of motion, which doesn't include time in it, because we weren't asked to solve for time. We were asked to solve for displacement. Because numerical values are not required, we still don't need to know the time. We just have to know, sort of that the momentum starts non-zero, but it ends up at rest, and so it goes to zero. Because there is a uniform electric field, and we already talked about uniform deceleration, the momentum is directly proportional to velocity. You may recall that momentum is the product of mass and velocity. And so as the velocity, uniformly decreases under that constant deceleration, the momentum goes down right along with it. And so it's just a straight line connecting, a non-zero initial momentum to a zero final momentum after some time. The name of the quantity that is represented by the gradient of this graph, and so we're rising, a change in momentum, we're running, a change in time, and the rate of change of momentum is the definition of force. So force is the quantity that is represented by the gradient of a momentum time clock. All right, moving right along with a really good microphone that picks up all the ambient noise in the lab. A beta minus particle now enters the electric field along the same initial path as the alpha particle and with the same initial speed, 4.1 by 10 to the 6 meters per second. Calculate the kinetic energy in joules of the beta minus particle at point A. So the equation for kinetic energy is 1/2 mv squared. We can look up that the mass of a beta particle is the mass of an electron. It's 9.11 times 10 to the negative 31 kilograms. And so we're just plugging that in for mass and plugging that in for velocity. So we get 1/2 9.11 by 10 to the negative 31 kilograms, the mass of a beta particle, times the velocity 4.1 by 10 to the 6 meters per second quantity. Quantity squared there. I'm going to do this calculation on the screen there. So we got 0.5 times 9.11 times 10 negative 31 times 4, 1, 1, 2, 3, 4, 5, 4.1 million squared equals. So you get 7.7 times 10 to the negative 18 joules. You get 7.7 by 10 to the negative 18. That's the kinetic energy of that beta particle. All right, so this question, state and explain the differences between the electric force on the beta minus particle in the electric field and the electric force on the alpha particle in the electric field. Many students lost marks on this because they didn't identify differences. They only maybe listed one, or they didn't explain sort of what the difference is, or they talked about other things besides the electric force. It's only really asking about the force there. So the force is in opposite direction, and the explanation for that is because they have opposite charges, they're going to be pushed in different directions by the electric field. The other difference is how much force each one feels. So a uniform electric field E is defined as the force per unit charge. The charge on an alpha particle is positive 2e. The charge on our beta minus particle is negative 1e. And so you have not just the opposite direction of the force, but you have twice the force acting on the alpha particle that you do the beta particle, because for every unit charge the particle possesses, it feels, that unit force, right? It's the force per unit charge. So twice the charge means twice the force. The beta particle is going to feel half the force of the alpha particle and in the opposite direction. Why? Because it has half the charge. So it's going to feel half the force. And it's oppositely charged, which means that's why it's going to experience it in the opposite direction. The final question says the beta minus particle is produced by the decay of a nucleus. State the name of another lepton that is produced at the same time as the beta minus particle. So a beta minus particle is an electron, and so you're going to get an antiparticle. The anti-neutrino goes along with that. This is Dr. Schleif, living the physics life. See you next time.